So I'm Mickael Accensi, working at Ifremer at the laboratory for ocean physics and satellite remote sensing. And so I'm going to present you the resource code marine data toolbox, and especially here the high resolution wave parameter dataset for the European shelf. And so this work has been done in collaboration with all the partners of the project. So the outline of my presentation. So I will start by describing you the sea states Aincast we have produced during the project. And then I will show you how we have performed the validation based on in situ data and remote sensing data. And then I'll finish with the data access through our web portal. So this Aincast goes from 1994 up to 2020. So it's 27 years Aincast, and it covers the European shelf from Gibraltar in the south up to Faroe Islands in the north. And so first, to create this mesh, we had to use bathymetry data, coastline data, and sediment map data. So here what we've used is, for the bathymetry, the EMONNet and the homonym bathymetry dataset. And so you can see an illustration on the map on the right of the merger of those two products on our mesh. And so here the color are showing the depths between 0 and 100 meters to highlight the accuracy of the depths in coastal waters. And so for the coastline, the contours have been designed based on the polygon from the OpenStreetMap database. And as I said, we have used a sediment map to have a grain size classification for the bottom friction, which is really important for the wave dissipation in coastal areas. And so here we have used the EMONNet and the SHOM sediment map. And we have an illustration below of the grain size classification on our mesh. And as you can see, the grain size can vary a lot depending on the areas, and especially in the channel. And so it has a strong impact on the wave dissipation. And so then we have forced the model with current and water level. And because there is, at the present time, no database for current and water level at high resolution covering the whole area of the resource code project, we had to use Tidal atlases. So here we have used the Ifremer and FES 2014 atlases. So on the image on the right, you can see the different Tidal atlases from Ifremer with different spatial coverage and resolution. So here the resolution goes from 250 meter for the coastal area up to 2 kilometers for the larger one. And so then we have recomputed those tidal constituents on our mesh node at a 30-minute time step. And you have an example on the map below of the tidal M2 amplitude interpolated. And so then we were able to use those tidal constituents to reconstruct the tidal currents and water level for every time steps of our Aincast. And then we have forced our model with wind. And so here we have used the ERA 5 global Aincast, which is a 1/4 degree resolution and hourly time step. And because we know that this Aincast has some bias for the extreme wind, we had to apply a correction to have more realistic wave results in high wind conditions. And so the model we use for the waves is a spectral wave model Weather 3. So here we've used the latest version 7.08, and we have developed during the project a new parameterization, which is a T475, which is fully described in the paper from Alde et al. 2021. And about the spectral resolution, here we have used 36 direction beams and 36 frequencies. And so it was a good balance between accuracy and computational time. And about the spatial resolution, so as you can see on the figures below, the mesh is a triangle-based mesh. And so The triangle size goes from 200 meters up to 10 kilometers, depending on the depth gradient and the coastline complexity. And so the mesh contains more than 330,000 nodes. And at the open boundary of our mesh, we have forced our model with a directional spectra from a global grid at half degree resolution, which use the same wave tree parameterization and the same wind forcing to keep a good consistency between the two models. And now about the output parameters. So we are outputting up to 39 parameters to fully describe the sea states. So we have the classical ones to describe the sea state, which are the significant wave height, the peak period, the energy fluxes, and many more. And we also have output for spectral partitioning to describe separately the wind sea partition and the different swell partitions. And we also output the forcings, which are here the wind, the water level, the current, and we also output the depth. So you have an example here on those time series at a given node, and so you can see here on the top one the significant wave height. On the middle, you have different wave periods, which are outputted by wave watch. And on the one below, you have the mean and the peak direction. So yeah, just a few examples of those 39 global parameters. And we also output the wave spectra. So we output the frequency spectra at each grid node at hourly time step. And we output the directional spectra at more than 24,000 locations. And so you have those locations on the map on the right. So it's a coarser grid, but it mainly covers the whole area of interest for comparison. And now I'm going to describe the validation we have performed to validate the database. So the validation was done per month, per year, and on the whole Hindcast. So here, this validation was done on using the CMEMS Institute TAC database. And so we have compared here 5 wave parameters, which are the significant wave height, the peak period, the mean period, the direction and the spreading. And on the table below, you can see the number of buoys and the number of samples we have used depending on the parameters, because we don't have the same availability of the data depending on the parameters. And so looking at the statistics, you can see that for most of the parameters, we have a really good correlation coefficient. And we have a pretty low bias also. And the normalized root mean square error is around 20%, except for the spreading, which has a lower score. But it's also more complicated to get accurate results. And so to give you an illustration on the map on the left, you can see the location of all the buoys we have used from the CMEMS Institute TAC for comparison. And here the colors are representing the root mean square error for the significant wave height. And so as you can see, the error is around 20 centimeters in average, which is very good score. We have also performed spectral validation, so with a smaller set of buoys which provide the spectral data. And so those locations are shown on the map here. And on the side panels, you can see the comparison of the recorded annual energy over the frequencies. So on the black line, you have the buoy measurement, and on the blue line, you have the model output. And so on most of the buoy comparison, we have a really good fit between the model and the buoys, except at some location which are circled in red on the map, where we have sometimes some slight over or underestimation of the model. And this is due to really sheltered area or really shallow water area. And so this validation was done for every year of the Hindcast, and they are all available in the dataset and also in the user manual. And finally, we have done a validation against remote sensing data. So here we have used the CCI C-State version 1 altimeter database. And so what we have done here, we have collocated the model output along each altimeter track. And on the table on the right, you can see the overall statistics per altimeter. So each line represents the statistics for each altimeter on the covered period. And if we focus on the last line, which is a merged product of all the colocalization for the period from 1994 up to 2018, you can see that the bias is really close to zero. And the error is about 30 centimeters in average, which represents 10% error. So that's really good results. And then if we look at the time series below, so you can see the statistics for every year of the Hindcast. And so each color represents an altimeter statistic. And if we focus on the black line, which is the merged product, you can see that it's pretty steady over the years. And it's with a slight improvement for the latest years. And on the maps on the left, you can see on the figure A the normalized bias. So here, all the statistics on the left are all for the world Hindcast, so for the 27 years. And so for the normalized bias, you can see that it's varying between -5 and +5%, with a trend to be more positive in the Atlantic Ocean and a bit more negative in the North Sea. And on the figure B, you have the normalized room mean square error, which is about 10% with a slight increase in the North Sea and in the coastal areas. And on the figure C, you have the number of matchups. So it can give you an idea of the amount of colocalized data we have used for the statistics. And on the figure D, you have the correlation coefficient, which is pretty homogeneous over the whole grid. And I haven't said, but for the maps here, we have averaged all the collocated data on a regular grid at 1/8 degree to have a spatial representation of the statistics. And so then about the data access, so you have two ways to access to the data, so either through FTP or through our web portal. So this Hindcast is pretty heavy because it represents up to 50 terabytes of data, which are stored in monthly netcdf files. So you can still download those files through FTP. Otherwise, we have performed an integration of those data in a time series oriented database, which is Cassandra. And then we have developed Python tools to be able to do requests on those data from the database Cassandra and do some extraction of the data and some advanced statistics and operations. So now I will explain you how to access to the data through the FTP and the web portal. So first, if you go on the laboratory website, which is UMR Labs, you can go in the section Data Waves Sextant, and you will access to our wave product catalog. So it looks like that. And so you will see different wave products. So you have the resource code product, you have the Homer product. So probably many of you know this product, which is a past project on the Bay of Biscay. And you have also the global Hindcast, which was used to force the resource code Hindcast. And so if we go on the resource code project, you will access to this main page. And here, so what we have two links on the top right here. So the first one, circled in red, is to access to the database user manual, and the second one is to access to the FTP. So if we check first to the database user manual, if you click here, you will access to this web page, and so you have an easy and open access to the database user manual. So you just have to click on the link here, circled in red. And so I will not show you the full content of the database user manual, but I will just show you a kind of summary. And so what is described here is the model description. So everything starting from the parameterization and the forcing fields, the bathymetry and everything. You have also the database organization. You have all the output parameters which are described and about the validation, so both the altimeter comparison and the in situ comparison. And you have a last chapter about all the recommendations. And so if we go back on the main page of the product, you will access to an access form that you have to fill in. And once you've sent it, you will have the link to access to the FTP. And so if we go quickly on this FTP, you will see that all the data are stored in yearly directories. And if we go on one yearly directory, you will see that it's stored by month. And it looks like that. So for example, here for January 1994, you have different directories. So the first one is the buoy. So you have all the comparison for this month against the CMEMS buoys. You have a field directory which stored all the global wave parameters. The Freg directory stored all the 1D spectra, and the SAT directory store all the altimeter comparison against the model. And you have the spec directory which stores all the directional spectra at the 24,000 output points. And the data directory contains all the configuration file we've used for the Ncast. And so, for example, here, if we look in the field directory, you will see that you can download the monthly netcdf file directly, but it's pretty heavy. So, for example, here, the monthly file, which contains the 39th wave parameters, is about 13 gigabytes. So you can download it, but it can be a bit heavy. So the other way to access to the data is to go on our website, which is resourcecode.ifrema.fr. So it looks like that. And if you go on the top right of the website, you will be able to access to different sections. So you can explore the data. You can access to some tools that Nicola will show you just after. And you can also access to the documentation. And just to quickly show you, if you click on Explore, you will be redirected to this user interface. And so you will be able to dynamically zoom on the mesh and select a node. And depending on the node, you will be able to output the wave parameters and play with some statistics and playing with the round and stuff like that. And then if you want to extract the data or do more sophisticated operation and statistics, you can just go in the tools and play with. So some references if you want to use our work and cite it. So there is a DOI for the database. And there is also a reference paper which was presented during the EW Tech conference last September. And we have also the user manual, which is available. And so to summarize this talk, so we have produced an open source C-States database covering the European shelf over the period of 1994 up to 2020, with a high level of quality and reliability based on validation against remote sensing data in situ buoys. And so this resource is now available through our web portal for an easy data access. And we will maintain the database with a yearly update to keep it up to date. So thank you for your attention, and I will now give the talk to Nicola.